m of x equal to little o of x is equivalent to mu of n over n equal to 0. We'll go in the easy direction first. We will first show that this sum implies that, and then we'll do that implies this, and that requires an idea to get exactly 0. Okay. All right. The next theorem is theorem 3 for us today. Yes. So summation mu of n over n from 1 to infinity with 0 implies m of x equal to little of x. So this is very easy. In fact, you don't even need to know that that is 0. The fact that that series converges is enough to show that m of x is little o of x. Or why? You see, if I had a 1 here, that series would diverge. Now this mu of n has value 1 and minus 1. Of course, it's got value 0 also. So for it to converge, the 1s and minus 1s must occur with approximately equal frequency to effect a cancellation. So that's really what is going on here to show that. Okay, so this direction is easy. We'll just show that by partial summation. Okay, so here's what we do. Put little m of x equal to summation mu of n over n less than or equal to x. And m of x can be written as summation mu of n over n times n, which of course is the integral t dm of t from 1 minus to x. Right? So that is t m of t 1 minus to x minus the integral 1 to x m of t dt. I differentiate the t. This is nothing but x m of x. I want you to, after finishing this proof, I'll make a comment. X m of x minus integral from 1 to x. This m of t is little o of 1 dt. This is little o of 1. So this together is little o of x. I have to make some comments here. 11. This is very small. Now I got to make some comments here. Why is this true? So remark. This is easy. This part is going to 0 as x goes to infinity, so this is, but simply because this is going to 0 as we go to infinity, why should that integral be little o of x? So we have to make this comment. Remark 1. If I have two functions, f of x is little o of g of x, and if the integral g of x, g of t dt, positive, this positive function, from 1 to infinity, diverges, then the integral of f of t dt from 1 to x is little o of the integral from 1 to x g of t. So this is, only this is in the divergent case, not in the convergent case. So what is the difference between a divergent integral? Only look at positive functions. What is the difference between a divergent integral involving a positive function and a convergent integral involving a positive function? In the case of a convergent integral, all the action is taking place in the beginning. The tail is of no consequence. But when you make a comment that f of x equal to little o of g of x, you are making that statement near infinity. Therefore, that has no consequence in a convergent integral. So for example, 1 over t cubed is little o of 1 over t squared as you go to infinity. But integral 1 over t cubed has a finite value. Integral 1 over t squared has a finite value. So how can you say one integral is little o of the other integral? They differ by a constant value. They treat it as integral because the contribution to the two convergent integrals is coming from the beginning, where the little o has no role to play.
The little o has only a role to play as you proceed to infinity. On the other hand, if this integral diverges, then that means all the action is taking place for large values, and that's why this is divergent. But for large values, this is small compared to this, therefore this integral will be a little lower this integral. It's an interesting, this will be one of your homework problems in general. But here, it's easy. You split this up into two integrals, 1 to square root of x, and square root of x to x. From 1 to square root of x, this is an order of magnitude no more than square root of x. For after square root of x, the argument is large, so the little o of 1 takes a role, plays a role, and therefore this is little o of x. Done. Now one more remark. Remark 2. It's not necessary that this series actually converges to 0. It does converge to 0, but it need not converge to 0. You can apply this method in another situation where maybe this simply converges to some constant c. Even for it to converge to a constant c, half the time your value must be +1 and half the time it will be minus, because otherwise it will explode and go to infinity, because summation 1 over n is divergent. So let's say 2/3 of the time it's +1 and 1/3 of the time it's -1. It's still going to go to infinity because of the density of the +1s. So they must be almost equal. So why? How is that shown in the proof? It's shown in the proof because if this converges to c, then that means this is not little o of 1, but this is c plus little o of 1. But here, when I subtract, I won't subtract little o of 1, I'll subtract c plus little o of 1. The c part will cancel. The same c. And only the little o of 1 remains. So make the second remark. Even if summation mu of n over n from 1 to infinity equal to c, some constant c, this would imply f of x is little o of x. I mean, this is only as a matter of principle, I'm saying. We can use it in other situations where we have other arithmetical functions whose sum of the reciprocal with 1 over n will converge to some constant, and then this little o of x behavior will come through. Alright, but now, in the last 10 minutes, we need to prove this fourth theorem. This requires an idea. M of x equal to little o of x implies summation mu of n over n 0. Okay, so the proof is going to make use, it has to use two ideas. Okay, so the proof uses two ideas. Okay, idea 1 is summation mu d of mu n, integral part of x over n less than or equal to x, is 1. This is an unbelievable identity. You really have to calculate this to believe that this is true. This is like saying, the first time I was told in calculus that as x tends to infinity, e to the minus x goes to 0, and they gave me this series. It was hard to believe, because when x is very large, the individual terms of the series are all huge. Some miraculous cancellation takes place. And the value is e to the minus x. And the only way you can prove that is to observe that that series enjoys the exponential property that if you call it f of x plus y is f of x times f of y, and consequently e to the, when you put x replaced with minus x, it has got to be e to the minus x. It's counterintuitive. The terms of the series are so huge, but the cancellation is miraculous. Same thing here. Everything cancels and only get 1. Why? Because summation mu d mu n, integral part of x over n, is the same as times summation 1 m less than or equal to x over numbers n which divide n, which is the same as summation m less than or equal to x summation mu n divides n. That sum vanishes at all values except n equal to 1, gives you 1. That's the reason why this holds. So what does this mean? Therefore, the sum of mu of n x over n can be written as summation mu of n integral part of x over n plus summation mu of n fractional part of x over n, which is the same as x times summation mu of n over n is 1 plus summation mu of n fractional part of x over n. I get nervous when 5 minutes before class all these doors are slammed. The other class are not utilizing the time to the fullest. Okay. All right, so we got this. So we need to show that is idea 2. That summation mu of n fractional part of x over n is little of x. So if you want, you can call it a claim. That's what I'm claiming. So not only is summation mu of n less than x little of x, but when I put a weight fractional part of x over n, that also is little of n. And you know the reason? The reason is the fractional part of x over n is not changing as much. The fractional part of x over n will be very nearly equal to the fractional part of x over n plus 1, except in some specific place where the reciprocal is an integer and a jump. But other than that, it's the same. All right, so how do we prove this? We actually compute this. Okay, so here's what we do. All right, let delta epsilon greater than 0 be given. Oh, we don't even need the epsilon greater. Okay, that's fine. Choose let delta be greater than 0 be small. Delta to be chosen soon. So let's call the sum just sigma. Decompose sigma as the sum of mu of n fractional part of x over n less than or equal to delta x plus summation mu of n fractional part of x over n, where delta x is less than n is less than or equal to x. So we'll call it sigma 1 plus sigma 2. Equation number 13. Clearly, sigma 1 is in absolute value is less than or equal to delta x. Each term is no more than 1 inside, so there's nothing there. So we have to calculate sigma 2. With regard to sigma 2, rewrite it as sigma 2 is equal to summation m of n minus m of n minus 1 fractional part of x over n. Okay? Just rewrite it that way. So this is equal to just do the endpoints. Right? M of x plus capital O of M of delta x plus summation M of n times fractional part of x over n minus
fractional part of x over n plus 1. Maybe I've got a sign mistake here, but I'm going to put absolute values. I'm going to put absolute values. I flipped this. Okay? You know, you see what I'm saying. I mean, there's an m of n minus n plus. I think I've got it right here, but it could be x over n plus 1 minus x over n. Just check that. Okay. Now, m of x is little o of x. This is going to be little o of delta x, right? We can just put no more than delta x here. It doesn't matter. Right? Now, this one is no more than the smallest, so this is m of x. So here it's epsilon, so I'm going to put epsilon of x. And now I'm going to have the sum x over n fractional part minus fractional part of n plus 1. Agreed? I've chosen the biggest possible size for m of x in absolute value. I've taken this out like this. And given m of x is little o of x. Now what is this? Epsilon of x plus delta of x plus epsilon of x. What is this? This is capital O of the integral from 1 to 1 over delta of d, fractional part of t, absolute. So you understand this? Total variation. The total variation of a function is the integral of absolute df. Going back to your real analysis course. So this is no more than the total variation of this function on the interval from 1 to 1 over delta. Because the largest value of x over n will be 1 over delta when n is smallest. So this is I'm chopping it out. So this is the total variation of the function. Now, the function fractional part of x is the sawtooth function. So the total variation is 1, then another 1, 1, and another 1, 2. So the total variation is no more than 2 times up to where you go. So this is less than epsilon of x plus delta of x plus epsilon of x times 2 over delta. I'm done. 14. So what is the choice of delta? I got to put delta equal to square root of epsilon. This is 2, not x squared. So choose delta equal to square root of epsilon. So I got square root of epsilon, square root of epsilon. This is absorbed in the square root. Epsilon x is smaller than square root of epsilon x. So this whole thing is no more than square root of epsilon x. That's really what I wanted to show. Proving plain. So there are 2 ideas that come here. One idea is the use of this marvelous identity, and I'll come back to this on Friday, assuming they don't close the university due to the storm. Okay? And then I will also talk about this idea. This leads to a general result called Axer's theorem. And I want to talk about the history of Axer's theorem. It's a very beautiful description in Hardy's final and classic book, Divergent Series, which according to Littlewood was the favorite book of Hardy. And it went to press. So Hardy saw it go to press, but Hardy did not see it in print. So Littlewood wrote the preface in the place of Hardy. And it's a 1-paragraph preface which you should read. It is compact, but it contains everything. It's power-packed and it is emotional. So it's a beautifully written preface to Hardy's book. He said this was Hardy's favorite. So we'll talk about some summability theorems and Axer's theorem. I may start the chapter on that. I'll finish this.